Two protons collide at 99.99999/100th of the speed of light. The collision lasts less time than it takes light to cross the diameter of a proton. Out of the debris fly hundreds of particles that did not exist a moment earlier, born from the pure energy of the impact. Each one must be caught, measured, identified. That takes milliseconds. There are 40 million such collisions every second. This is how the Large Hadron Collider works. And this is how we learn what matter is made of. This is more or less what particle physicists do, except the things they smash are not clocks but protons. And the energy involved is not a drop from your hand to the floor. It is the energy of millions of volts concentrated into objects smaller than an atom by a factor of 10,000. And the machine that does the smashing is not gravity. It is the Large Hadron Collider, a ring of superconducting magnets buried under the Swiss and French countryside, 27 kilometers in circumference, the largest scientific instrument ever built by human beings. But here is where the analogy between a clock and a proton breaks down, and breaks down in a way that changes everything. When you smash a clock, the pieces you find are the pieces that were already there. Gears come from gears. Springs come from springs. Nothing new is created. But when you smash protons together at high enough energy, something extraordinary happens. Particles appear that were not inside the protons to begin with. They are born from the energy of the collision itself. They are conjured out of pure kinetic violence. New objects never seen before, materializing from the mathematics of Einstein's most famous equation. Energy and mass are interchangeable. Give a collision enough energy, and nature will spend it on creating things. This is why particle physicists love their accelerators. They are not just microscopes, they are also factories. They make things. And the things they make have taught us something so surprising, so elegant, and at the same time so deeply unsettling that the field has been arguing about it ever since. Let's start from the beginning. The world is made of something. This is not a profound statement. It is almost embarrassingly obvious. You, the chair you are sitting in, the air around you, the light reaching your eyes, all of it is made of something. The question physicists have been asking for centuries is, what is that something exactly? How deep does it go? In the 19th century, chemists cracked the first layer. The universe at its chemical level is made of elements: hydrogen, oxygen, carbon, iron, about 90 naturally occurring varieties, each with its own personality, its own tendency to combine or refuse to combine with others. Mendeleev arranged them in his table. It was one of the great achievements of human intellect, order discovered in what looked like chaos. But elements were not the bottom. The 20th century peeled back the next layer. Every element is made of atoms. Every atom has a nucleus at its center, surrounded by a cloud of electrons. The nucleus itself is made of protons and neutrons, packed together by forces so strong that splitting them releases the energy of nuclear weapons and nuclear power plants. So, electrons, protons, neutrons, three types of things, surely this is the bottom. It was not. The second half of the 20th century revealed that protons and neutrons are themselves made of smaller objects, quarks. And the story of how physicists figured this out is the story of a civilization deciding to study its own existence at the deepest possible level. Today, our best description of the fundamental constituents of nature is called the Standard Model. It is not a modest name, and the theory is not a modest achievement. It is probably the most precisely tested scientific theory in human history. It has made predictions that have been verified to 9 decimal places. 9. That is the equivalent of measuring the distance from Moscow to New York and getting it right to within a millimeter. The Standard Model says that all matter in the observable universe, everything we can see, touch, measure, or detect, is made of exactly 2 types of fundamental particles: quarks and leptons, and these come in only 12 varieties, 6 quarks, 6 leptons. That's it. The quarks have names that sound like they were invented by a committee of physicists who had just discovered poetry. Up, down, strange, charm, bottom, top. The leptons include the electron, which you know from every electrical device ever made, and 5 relatives, including 3 types of neutrino, ghostly particles that pass through the Earth as if it were not there. Now here is the remarkable thing. Of those 12 particles, only 3 of them are needed to build everything you have ever seen with your own eyes. The up quark and the down quark make protons and neutrons. The electron surrounds the nucleus. 3 particles. The rest were discovered in accelerators and cosmic rays. They appear briefly, decay into something lighter, and vanish. They were common in the early universe, when temperatures were unimaginably high. Today, they are relics or laboratory curiosities. Nature, it seems, was extravagant. It built 3 entire generations of matter, each an exact copy of the previous one, except heavier. A muon is essentially a fat electron. A strange quark is essentially a heavy down quark. Why 3 generations? Why not 1? This is one of the questions the standard model cannot answer. It describes the pattern but does not explain it. But matter is only half the story. The other half is forces. 4 fundamental forces govern everything that happens in nature. 4, and only 4, at least as far as we know. Gravity holds galaxies together and keeps you on the surface of the Earth. Electromagnetism governs light, chemistry, and every electrical device. The strong nuclear force holds quarks inside protons and neutrons. The weak nuclear force is responsible for a certain type of radioactive decay, and crucially for the nuclear reactions that power the sun. Without these forces, matter is just inert. It is the forces that make matter do things. Now here is one of the most beautiful ideas in all of physics. Forces are not mysterious influences that reach across space. They are also made of particles. When 2 electrons repel each other, they do it by exchanging a photon, a particle of light. The photon is the carrier of the electromagnetic force. The strong force is carried by particles called gluons. The weak force is carried by the W and Zhou bosons. Every force has its messenger, and every messenger is a particle. This is the quantum picture of reality, particles interacting by exchanging other particles the way people might exchange letters or blows, and those exchanges determining everything that happens at the microscopic level. The photon is massless. It can travel infinite distances. This is why you can see stars millions of light years away. Their light is carried by photons that have been traveling for millions of years. The W and Zhou bosons, by contrast, have mass. They are heavy, and heavy messenger particles can only carry their force over very short distances, shorter than the diameter of an atomic nucleus. This is why the weak force is weak. It is short-ranged. It acts only in the intimate contact of subatomic collisions. The gluon is massless too, like the photon, but it behaves in a way that defies intuition. Gluons carry the strong force, and the strong force does something no other force does. It gets stronger as you try to pull quarks apart. Quarks can never be liberated. They are permanently confined inside protons, neutrons, and other composite particles. You can never isolate a single quark in a detector. The moment you try, the energy you put in goes into creating new quark-antiquark pairs, and the quark you thought you were pulling free is immediately surrounded by new companions. So the universe at its deepest level is a world of quarks and leptons, exchanging gluons and photons and W bosons and Z bosons, perpetually interacting, always in motion, always changing. This is the standard model, 12 matter particles and 4 force carriers. An astonishing economy of means for such a rich and varied cosmos. And then, in 2012, a 5th force carrier was discovered. It was announced on the 4th of July. Perhaps intentionally, the auditorium at CERN was standing room only. Physicists had flown in from all over the world. Peter Higgs, the 83-year-old Scottish physicist who had predicted this moment almost half a century earlier, sat in the audience with tears in his eyes. The particle they announced was the Higgs Boson, and its story is one of the strangest and most beautiful in the history of science. To understand why the Higgs boson exists, you have to understand a problem. The Standard Model is built on symmetry. Symmetry in physics is not just an aesthetic concept, it is a mathematical principle with physical consequences. Emmy Noether proved in 1915 that every continuous symmetry in physics corresponds to a conservation law. The symmetry of time, the fact that physics is the same today as yesterday, gives you conservation of energy. The symmetry of space. The fact that physics is the same here as a meter to your left gives you conservation of momentum. The Standard Model has deep internal symmetries too, and these symmetries, when you examine them carefully, do something strange. They forbid particles from having mass. If those symmetries were exact, every particle in the Standard Model would be massless, like the photon. The universe would contain nothing but massless particles racing around at the speed of light. There would be no atoms, no nuclei, no chemistry, no stars, no us. Clearly, the symmetries are not exact. Something breaks them. This is what the Higgs field does. It pervades all of space, the way air pervades a room. And particles interact with it as they move through it. They are, in a sense, dragged by it, slowed down, given inertia. What we call mass is, in this picture, the resistance a particle feels as it moves through the Higgs field. The more strongly a particle couples to the field, the heavier it is. The top quark, the heaviest known fundamental particle, couples to the Higgs field far more strongly than the electron, which is why the top quark is 300,000 times heavier. The photon does not couple to the Higgs field at all. This is why it is massless. This is why light always travels at the speed of light. The Higgs boson is the quantum of the Higgs field, the particle you get when you knock the field out of its equilibrium and watch it vibrate. Confirming its existence was confirmation that the field itself is real, that the mechanism by which particles acquire mass is real. This was not an easy discovery. The Higgs boson is a strange, retiring particle. It decays in less than 1,000th of a millionth of a millionth of a millionth of a second. It is produced very rarely in proton collisions. And it can decay into many different things: pairs of photons, pairs of Z bosons, pairs of bottom quarks. You can never see the Higgs directly. You can only see its decay products, and you have to be very clever to recognize them as coming from the Higgs at all. It took tens of thousands of physicists, 2 enormous detectors the size of apartment buildings, and decades of work to find it. But they found it. Now the Standard Model is complete. 12 matter particles, 5 force carriers, the gluon, the photon, the W boson, the Z boson, and the Higgs boson. A complete inventory of what the universe is made of and what forces act on it, or so it seems. Because here is the thing. Completing the Standard Model did not resolve the deepest questions. It sharpened them, and to understand what those questions are, we have to talk about something that sounds almost absurd. The fact that different numbers in physics are suspiciously, improbably, maddeningly different. Consider 2 numbers. The first is the mass of the Higgs boson, about 125 GeV, roughly 125 times the mass of a proton. This is the energy scale of the weak force, the scale at which the Standard Model operates in everyday particle physics. The second number is called the Planck mass, the energy scale at which gravity becomes as strong as the other forces. This is where quantum mechanics and general relativity must meet, where a complete theory of quantum gravity would operate. The Planck mass is about 10 raised to the power of 19 GeV. The ratio between these 2 numbers is 10 to the 17th power, 100 million billion, written out 100 million million to 1. Why does this matter? In quantum field theory, particles do not exist in isolation. They are constantly interacting with the quantum vacuum, a seething sea of virtual particles that briefly pop into and out of existence. These interactions affect the particle's properties, including its mass. They add quantum corrections. And for the Higgs boson, these corrections are enormous. In the absence of any controlling principle, they would be on the order of the Planck mass. They would drag the Higgs mass up by 17 orders of magnitude. But the Higgs boson is not Planck mass heavy. It is a mere 125 GeV. Something must be canceling those gigantic corrections to astronomical precision. Either the universe performed a miraculous fine-tuning of its own parameters to 17 decimal places, or there is something we do not understand. This is the hierarchy problem. It is not just an aesthetic complaint, it is a genuine indication that our picture of physics is incomplete. The standard model, for all its extraordinary precision, is missing something. There is new physics out there. Physics we have not yet discovered, and it is responsible for keeping the Higgs boson light. The most popular candidate solution is called supersymmetry. Supersymmetry, SUSY as physicists call it, is a new kind of symmetry. Every known symmetry relates things of the same type. Rotational symmetry rotates space into space. Time translation symmetry shifts time forward or backward. But supersymmetry does something unprecedented. It relates particles of different types. Specifically, it relates fermions, particles with half-integer spin, like quarks and electrons, to bosons, particles with integer spin, like the Higgs and the photon. If supersymmetry is a law of nature, then every particle we know has a superpartner, a twin that differs in spin by 1/2. The superpartner of the quark is the squark. The superpartner of the electron is the selectron. The superpartner of the photon is the photano. The superpartner of the gluon is the gluino. Even the Higgs boson has a Higgsino. These names are not jokes, though physicists evidently enjoyed inventing them. Now, why would this help with the hierarchy problem? Because in a supersymmetric theory, the quantum corrections to the Higgs mass from fermionic virtual particles are exactly cancelled by the corrections from their bosonic superpartners. The enormous numbers that threaten to drag the Higgs mass to Planck scale values cancel out, leaving a Higgs mass that is naturally small, not because of miraculous fine-tuning, but because of symmetry. This is why theorists love supersymmetry. It is not just elegant, it is useful. It solves a real problem. And it predicts testable consequences. If supersymmetric particles exist, they should be producible in accelerators. Their masses should be of the same order as the Higgs mass, a few hundred GeV, maybe a few thousand. Within reach of the Large Hadron Collider, supersymmetry also offers a bonus. Among all those supersymmetric particles, the lightest one, the neutralino, a neutral combination of the photino and Higgsino, would be stable. It would not decay into anything lighter. And it would interact only weakly with ordinary matter. This makes it a perfect candidate for dark matter, the invisible substance that outweighs all the visible matter in the universe by a factor of 5. So, supersymmetry would simultaneously explain the hierarchy problem, provide a dark matter candidate, and help unify the forces. It is almost too good. It was always considered the most likely discovery waiting for us at the LHC. But it has not been found. This is the central drama of contemporary particle physics. When the Large Hadron Collider turned on, optimism was enormous. Run it for a few months, and supersymmetric particles would come tumbling out. The photino, the squarks, the gluinos, they would appear in the data, their signatures unmistakable. The Higgs boson would be found, and then, almost immediately, the new physics that explains why it is so light. What happened instead was the Higgs boson, exactly as predicted by the Standard Model, with properties exactly as the Standard Model specifies, and nothing else. No supersymmetric particles. No new resonances. No signs of extra dimensions. No indications of composite structure. The Standard Model performed flawlessly. and the silence beyond it was deafening. This was not expected. By 2012, the LHC had been running for 2 years. Theorists had expected the superpartners to show up immediately. Instead, nothing. The collider then ran at higher energy. Still nothing. Run after run, more data, more collision events, more careful analysis. The standard model kept being right. New physics kept being absent. This was not just disappointing, it was philosophically disorienting. The hierarchy problem is real. The corrections to the Higgs mass are real. They should be compensated by something, but whatever compensates them, it is apparently not within the reach of the LHC. Either the new physics is at a much higher energy scale than expected, in which case we may never access it with any foreseeable accelerator, or the standard model is somehow mysteriously correctly fine-tuned, and we are wrong about what counts as natural. And so the field arrived at a crossroads. On one side of the crossroads stands the traditional view. Nature is mathematically natural, meaning that quantities of the same type should be of similar magnitude unless there is a symmetry reason for them to differ. The hierarchy is an embarrassment that demands an explanation. Keep building bigger accelerators. Keep looking for new physics. It is there, we just have not found it yet. On the other side stands an idea that many physicists find deeply uncomfortable: the anthropic principle. The anthropic principle in its scientific form is not a mystical claim. It is a statement about selection. It says, we observe the universe from a position that is not random. We are observers, and observers can only exist in regions of the universe, or in versions of the universe, where the physical constants allow observers to exist. Think about where you live. You live on the surface of a planet, in a solar system, in a galaxy. If you were placed randomly in the entire volume of the universe, the overwhelming probability is that you would end up in the void between galaxies, cold, dark, no air, no matter. But you are not in the void. You are here, because here is where observers can be. The selection effect is obvious. The anthropic principle applies the same logic to the physical constants themselves. Consider the cosmological constant, the energy density of empty space, which is driving the accelerating expansion of the universe. This number is absurdly small, not just small, small with a precision that beggars belief. In natural units, it should be of order 1. In reality, it is about 10 to the minus 120. That is a fine-tuning of 120 decimal places. No theoretical mechanism has ever been found to explain this. But here is what we do know. If the cosmological constant were 1,000 times larger than it is, still utterly tiny by the standards of particle physics, the universe would have expanded so rapidly in its early history that galaxies could never have formed. No galaxies means no stars. No stars means no heavy elements. No heavy elements means no planets. No planets means no us. The cosmological constant is small enough for us to exist, and we exist. Therefore, we observe it to be small. The argument is circular, but the circularity is meaningful. The same argument applies to the Higgs mass. If the weak scale, the energy at which the Higgs field becomes relevant, were much larger than it is, the weak force would become too weak to drive the nuclear reactions in stellar cores. The sun would go cold. No sun, no us. If the weak scale were Planck scale, large gravity inside compact objects would be so intense that every sufficiently massive lump of matter would collapse into a black hole. The universe would be a cemetery of black holes. The Higgs mass is what it is, within a range that allows stars to burn, planets to form, and observers to evolve. We are here to notice it. This is the landscape picture of physics. In this view, there may be no deep reason why the constants have the values they have. The universe may be vast, far larger than we can observe, and in different regions of it, the constants may take different values, perhaps governed by quantum fluctuations during inflation. Most of those regions are sterile. Our region is not. We are here because we had to be somewhere. This is not a comfortable picture for theorists. It suggests that some of the deepest questions they have been trying to answer, Why is the Higgs mass so much smaller than the Planck mass? Why is the cosmological constant so tiny? May not have the kind of elegant mathematical answers they have been looking for. The answer may simply be because you would not be here to ask otherwise, and yet, this view is difficult to falsify. We are here. That is an experimental fact. If the constants were different, we would not be asking the question. There is something genuinely scientific in noticing that our own existence constrains what values of the constants we could possibly observe. The question is whether this reasoning is the best we can do, or whether it is a surrender, an admission that theoretical physics has reached its limit and can no longer explain the world it describes. There is another class of things we know are out there, but cannot account for within the standard model. Dark matter. The evidence for dark matter is overwhelming and comes from completely independent directions. The rotation curves of galaxies are wrong. Stars at the edges of galaxies rotate too fast for the amount of visible matter present. The gravitational lensing of distant light is too strong. The large-scale structure of the universe, the way galaxies cluster and filament, cannot be reproduced in simulations without a large component of invisible, non-luminous matter. The universe is about 5 parts dark matter to 1 part ordinary matter. Whatever dark matter is, it is the dominant component of matter in the cosmos. What the standard model cannot tell us is what dark matter is made of. The leading candidates are hypothetical heavy particles, weakly interacting massive particles, or WIMPs. They would be produced in the early universe, when temperatures were high enough to create heavy particles. As the universe cooled, they would freeze out, stop interacting quickly enough to remain as a relic population. Their abundance today would be roughly what we observe, for particle masses in the range of tens to thousands of GeV. This is the WIMP miracle. The dark matter abundance comes out right without any additional tuning. Supersymmetric theories naturally produce such a particle, the neutralino. This is another reason supersymmetry was so appealing. It predicted dark matter without trying to. But the direct detection experiments that have been searching for WIMPs, enormous tanks of liquid xenon buried deep underground to shield them from cosmic rays, have been finding nothing. Experiment after experiment, more sensitive than the last, has come up empty. Either WIMPs are lighter or heavier than expected, or they interact more weakly than the simplest models predict, or they are not WIMPs at all. Dark matter may be something completely different. Actions, ultralight particles proposed originally to solve a problem in the strong force. Sterile neutrinos, hypothetical heavy cousins of the known neutrinos. Something we have not imagined yet. The universe knows, we do not. And there is the matter of matter itself. The standard model treats matter and antimatter almost symmetrically. For every quark, there is an antiquark. For every electron, a positron. When matter and antimatter meet, they annihilate. They transform entirely into energy, into photons. The standard model predicts that matter and antimatter should have been produced in equal amounts in the Big Bang. But here we are, made of matter, surrounded by matter. As far as we can tell, the observable universe contains essentially no primordial antimatter. Something broke the symmetry. There must have been, at some point in the early universe, some process that produced slightly more matter than antimatter, perhaps 1 extra particle of matter for every billion particle-antiparticle pairs. When the pairs annihilated, that small excess remained. We are the leftovers of a cosmic catastrophe of annihilation. The standard model contains a small amount of matter-antimatter asymmetry, the CP violation measured in the decays of cons and B mesons. But this asymmetry is far too small to account for the observed excess. Something outside the standard model is responsible for our existence. Whatever it is, it generated the conditions that allowed matter to survive the annihilation and become galaxies, stars, planets, and people. So, the standard model is the most precisely tested theory in science, and it is almost certainly incomplete. It cannot explain dark matter. It cannot explain the matter-antimatter asymmetry. It cannot explain why the Higgs mass is so much smaller than the Planck mass. It cannot account for gravity at the quantum level. General relativity, our theory of gravity, is entirely separate from the standard model, and any attempt to merge them leads to mathematical absurdities. This is the situation. Theorists know that something is missing. They do not agree on what it is. The experiments designed to find it have not found it, and the candidates that seemed most promising, supersymmetry in particular, have not materialized. Full chaos and discord in theoretical minds. But this chaos is not despair. It is the productive confusion that precedes a genuine discovery. The history of physics is full of moments when the old picture was clearly wrong and the new one had not yet arrived. The ultraviolet catastrophe at the end of the 19th century, the failure of classical physics to describe black-body radiation, seemed like an annoying loose end. It was the door to quantum mechanics. The inconsistency between electromagnetism and Newtonian mechanics seemed like a technical problem. It was the door to relativity. What is behind the door now? One possibility: nature is supersymmetric, but the superpartners are heavier than we expected. The hierarchy problem is real, but its solution operates at energies the LHC cannot reach. Future accelerators, a proposed 100-kilometer collider in China, or the future circular collider at CERN, might reach those energies. We have to wait decades and billions of dollars, and we might find what we are looking for. Another possibility: the hierarchy problem is real, but supersymmetry is not the answer. Perhaps the Higgs boson is not a fundamental particle after all. Perhaps it is composite, made of smaller things bound together by a new force, the way a proton is made of quarks bound by the strong force. This is called compositeness or technicolor. It has its own difficulties, but it has not been definitively ruled out. Another possibility: extra dimensions. The idea that space has more than 3 dimensions, with the extra ones curled up too small to detect except in high-energy collisions, has been a popular candidate for decades. Extra dimensions could dilute gravity, explaining why it is so much weaker than the other forces. They have specific, testable signatures at the LHC. Those signatures have not appeared, but the models have enough freedom that they are not entirely ruled out. Another possibility: we are wrong about the problem. Perhaps the hierarchy problem is an artifact of how we are thinking about it. Perhaps there is a new principle, a symmetry we have not discovered, an organizing idea we have not imagined that makes the Higgs mass natural for reasons we have not yet understood. This has happened before. Dirac predicted antimatter not because he was looking for it, but because his equation demanded it. Perhaps the answer is sitting in our existing mathematics, waiting for someone to look at it correctly. And another possibility, the uncomfortable one: perhaps the landscape is real. Perhaps the constants are what they are because we are here and there is no deeper explanation. Perhaps theoretical physics in some domains is not going to give us the beautiful unified answer it promised. Perhaps we have to accept that some numbers are just numbers, survivors of a cosmological selection process that we can observe but not predict. This is not a defeat, it is a repositioning. If the landscape is real, the questions shift. Not, why are these constants what they are, but what is the mechanism that generates the landscape? What is the structure of the space of possible universes? What selects our particular corner? These are hard questions. They may not be answerable with current technology, but they are real questions with mathematical content, and physicists are thinking hard about them. Meanwhile, the Large Hadron Collider keeps running. When it restarts at full design energy, it will produce collisions that have never occurred in a laboratory before. It is not impossible that something unexpected is hiding there, something that was not produced at lower energies, something that no theorist predicted because it is outside the space of ideas anyone has explored. The history of physics is also full of discoveries that nobody predicted because nobody was thinking in the right direction. Dark matter searches continue underground, in the deep quiet of mine shafts, where the rock filters out cosmic rays and leaves only the hypothetical heavy particles, which should occasionally knock a xenon nucleus hard enough to leave a trace of light. So far, silence. But the detectors are getting bigger. The sensitivity is increasing. If WIMPs exist and are anywhere near the predicted mass range, they will eventually be seen. Gravitational wave observatories are open for business, and they are hearing the universe in a new way. The rumble of merging black holes, the inspiral of neutron stars. These events produce conditions that existed in the early universe, and they probe general relativity in regimes never tested before. Perhaps they will show us something the standard model does not explain. Neutrino experiments are probing one of the deepest mysteries in particle physics, the masses of neutrinos, which should be exactly zero in the simplest standard model, but are not. The measurement of neutrino masses required an extension of the standard model. Why are they so tiny? A millionth of the electron mass or less? Some mechanism suppresses them. What is it? The universe is not silent. It is generating data constantly from every direction. We are learning to read it. Here is the situation, stated plainly. We have a theory, the standard model, that is essentially correct up to energies of a few hundred GeV. It correctly describes 12 fundamental particles and 4 fundamental forces. It has been tested to extraordinary precision. It is almost certainly incomplete. We know it must be incomplete because it cannot account for dark matter, for the matter-antimatter asymmetry, for gravity at the quantum level, and, perhaps most troublingly, for its own stability at high energies. The Higgs boson should be much heavier than it is, unless something is preventing those enormous quantum corrections from accumulating. We do not know what that something is. The candidates, supersymmetry, extra dimensions, compositeness, have not shown up in experiments where they were expected. Either they exist at higher energies than we can currently reach, or they do not exist at all. This puts physics in a genuinely uncertain position. Not a crisis. The standard model still works. But a moment of deep uncertainty about what comes next, and whether the ideas we have been developing will survive contact with new data. And this is, in a strange way, exciting. Because the most dramatic discoveries in science have always come at moments like this, when the map runs out, when the standard explanation stops working, when physicists sit in conference rooms and argue genuinely uncertain, pulling at threads that might unravel something magnificent or lead nowhere. There is a quote attributed to Richard Feynman, who had a gift for cutting through to the heart of things. He said, "It is possible that the universe has a beautiful underlying theory, and we will find it. But it is also possible that the universe is like an onion, layer after layer, with no bottom, no final explanation, no place where everything becomes simple. Both possibilities are, in some sense, extraordinary. One tells us that nature is organized around a few perfect principles. The other tells us that reality is genuinely infinite in its complexity, always yielding something new to whoever is curious enough to look. We do not know which universe we live in. What we know is that we are 12 fundamental particles and 5 force carriers away from where we were a century ago. We know that those particles are held together by 4 forces, possibly 5, possibly more. We know that the Higgs boson exists, that it gives mass to everything else, and that it sits at the center of a hierarchy problem that may be the most important clue we have ever had to what physics looks like beyond what we can currently see. And we know that thousands of physicists around the world are thinking about this right now, in offices and coffee shops and train stations, and at 4 in the morning when the calculation is almost done, with a mix of frustration and excitement that is the emotional signature of a field on the edge of something. The universe has given us enough to work with, just barely enough to see that there is something more, and not quite enough to see what it is. That gap between what we know and what we can almost see is where science lives. It is where physics has always been most alive, And so, with full chaos and discord in theoretical minds, and the LHC running and detectors listening, and mathematicians exploring geometries that may or may not correspond to reality, we wait, we calculate, we argue, we look. What comes next? Only the universe knows.